Hey, you should know the reason why you are here today. Why this session is needed. So much complexity in solving questions. Good evening, everyone. I am Sarika Purohit from Indore Institute of Science and Technology, and I will be host of your today's session. There are great lines that every code is simple but with correct complexities. DS is bit interesting without DS is not interesting without prior and good knowledge of time and space complexities. It is one of the smallest topic, but it is very important concept also. So here we are with this session, which will be full is of complexities and much more of learning. Did you also overwhelmed by complexities? No need to worry. Today we have our speaker, Mr. Shashwat Jaiswal sir. He had so many achievements, and some of them are he is GDSC lead, educator at CODECHEF, ICPC 1920 regionalist, and much more. I would like to call Shashwat sir to please enlighten our session with your knowledge. Over to you, sir. Please, sir.
Yeah, thank you, Sarika, and thank you for inviting me here. As you know, today's session is on time and space complexity, and this is, of course, a very important topic that everyone should be well versed with. However, let's begin gradually. So, first, let me brief you with a brief introduction about myself. I am Shashwat, and right now, I am interning at Google India. And before this, I have been, as part of the Google Summer of Code last year, CodeChef educator as well, then MITACS GRI scholar at the University of British Columbia in Vancouver, and also a DAAD wise scholar in Germany. So also, I have been working on an LFX project as an LFX mentorship on the anomaly detection engine. So it's like quite a few things, as well as my uh, usual engagements with competitive programming, with decent performances in Code Jam or the ICPC 1920 regionals. So yeah, that's the brief about me. If you need some more info on any of this, or you need some help regarding any of this, feel free to reach out to me. So for today, we have on the agenda time and space complexity. So when you talk about complexity, you the first thing you think is that why do you need to talk about complexity? And that being said, when you write down a code, you should have some metric of evaluation which tells you how good or how bad that piece of program is. For example, um, a program may run very fast on your computer for whatever inputs you might give, but it may explode to a very poor performance in real world, right? So we need to have some formal, standard, and unambiguous metric of evaluation which tells us how good or how bad a program is. All right. So how do you quantify good? For example, if you have a car, or if you're going to buy a car, what how do you quantify whether it's a good fit for you or not? You check the price, then you check the mileage, right? The fuel efficiency, then maybe you check the maintenance cost, and then is when you decide which car to go for. Similarly, when you think of an algorithm, you are bounded by two resources. And what are those two resources? It is namely, first is time, and the second is space, right? So now talking about time and space, we should always think of these as the two resources we want to save. All right. And often saving one comes at the cost of trade-off for the other, right? Okay. So okay. So what is time now here? Time is the number of, you can say, the number of clock cycles it takes for your code to run on the processor, and space is the amount of RAM or memory it consumes. All right. So whenever you open a problem, let's say on Google Code Jam or Kickstart or maybe on Code Forces or Lead Code, it always tells you that you have a time of 1 second, right? You must have seen this, right? Like it must have written something like this: time of 1 second, memory of, let's say, something like this, right? So what is this basically, and what is this? So as I said, this is the amount of time the program takes to run on a standard CPU, and this is the amount of memory consumed. All right. So coming back to our introduction of time and space, one thing should be very clear is that, so why do we need these? I mean, so you must have observed throughout your education is that time is measured in seconds. Okay. But can we measure time in seconds here in terms of computational complexity? The answer is no. Why is this a bad metric? It is because the amount of seconds required, or the absolute face value of time required for a logic to execute on one processor or on one computer, differs from another computer, right? So for example, okay, let's say you have a very good supercomputer, which can run a program in, let's say, 1 second, and the same program in your own laptop may run in 5 seconds, all right, maybe 20 seconds, right? So it depends on the computational power of your machine, then it depends on the background tasks running, and how much sharing of the CPU and memory is being done, how many concurrent processes are running, and all those things. Okay, this is why seconds, or the absolute metric of time, is a bad metric. So instead, what do we see? What do we use to quantify time complexity? It is the number of instructions. All right, number of instructions, and that too in a very clever way. Okay, so let's go over this. So for this, okay, so when we say number of instructions, okay, when you say number of instructions, what do we mean? We mean, for example, we have a program I is equal to 0. Okay, let's say this is a statement. This can be counted as one instruction. Okay, then let's say we have another statement, I plus is equal to 1. This is another instruction. So if this is our program, you have two instructions, right? So we can roughly say a program having one instruction compared to a program having two instructions, this will take more time in general. Okay, this is more costly, right? Okay, so now talking about a more complex programs, right? Let's say you have a loop, and then you are doing something like x is equal to x plus 1, right? So how many instructions will this have? This will go on for 10 times. So this statement executes 10 times. Similarly, this executes one time. This executes, let's say, how many? 11 times, right? This executes 10 times, or rather, you can say 11 times. Okay, right? So what do we end up with? This entire thing is equal to how many instructions then? 11 into 2 plus 1 plus 10, right? So this comes to around 33 instructions. Okay. Now, if we talk about a loop, which you can say something like a general loop, and then some statement. Okay. Let's say one, or let's say X number of statements, right? Oh, okay. Let's say one statement. Okay. One statement, right? So how much time will this take? This statement goes around n times. Okay, this goes n plus 1 times, this goes n plus 1 times, this goes 1 time. So what do we end up with? 3n plus 3, right? Total number of instructions. Yeah. Okay, so this is how we quantify the time complexity in terms of the number of instructions the program has to execute. All right, now, as you might expect, your programs can have hundreds and thousands of operations, and counting all of these operations like this may not be a very practical approach, given that you have multiple nestings and multiple function calls everywhere. Counting operators like this would not be a very practical approach to quantifying the time complexity. So, for this reason, what do we want? We want a somewhat more standard and less dependent way. Okay. So what do? We actually define a notation which is called the big O notation. Okay. So let's okay. Okay. So the big O notation actually gives the asymptotic bounds of our number of operations. Okay, the program has. All right. So when we say big O, we means what do we mean? So let's discuss this. All right. So big O basically gives you the order of the complexity of the logic you're implementing. Okay, of the algorithm. All right. So how you define it formally is something like this. Uh, Order of function of n, okay, where n is the size of the input. Okay, so this has to be greater than equal to actually this goes something like this. No, yeah. So you have, if you think about it, it is more of an approximate uh, level of comparison. So if you talk about this, so here you are dependent on these constants, right? 3n plus 3, right? So as you might expect, this equation might get very complex, and you may not always have uh, a strong way to reflect your equation, right, or your expression of number of operations. So how big O notation helps us is by making it a standard way, or defining a standard terminology in which we can quantify these expressions. All right. So to give you the intuition first and move to the definition later on, I will just probably make a column here, right? And let us see. So if you have something like 3n plus 3, this maps to order of n. All right. If you have something like 2n squared plus 5, this maps to order of n square, right? You must, most of you would be very familiar with this notation, right? But today we will discuss a bit more in detail about it, how to analyze programs for time complexity, and also how do we formally interpret big O. All right. So just give me a moment. Okay, so you can think of it to be something like this. So you have this function or this expression, and then you have this expression here inside the O, right? So if you say gx belongs to order of fn, all right, so you can think of this O to be a set, okay, or most likely an infinite set, okay, without bounds, and whichever expressions belong to this set for a given fn actually have a limiting upper bound. Let's get into the details of that. So when you have gx, when you have, sorry, gn, this will be gn. When you have gn, when you have fn, what you mean essentially is that some k times fn. Okay, so any function which actually is a member of order of some function should satisfy this inequality for any constant k. So if you can find any one constant k where this inequality holds, we are good. All right. Okay, so let's talk about it. So when I say this, let's pick this one. Okay, so this is our what? Gn. This is our Fn. All right. So, right, 3n plus 3 less than equal to k times n. So if you imagine here, if we pick, let's say k is equal to 10, right? If we pick k is equal to, let's say, 10, what happens? We get 3 less than equal to 7n. Okay, and for n greater than equal to 1, this is always true. Okay, so now let us define formally the big O notation, and then we will get to the more intuitive parts of it. A function fn belongs to order of gn if and only if fn is less than equal to k times gn and there exists k greater than 0 for every n greater than 0. Okay, so what this says basically is that a function fn will only belong to order of gn if this holds for any k, even if 1k we have, that's okay. Okay, for 1k for every n greater than 0, or we can say vice versa as well, but for now let's stick to this. Or you can have n greater than not 0, you can have something like n greater than n naught. Okay, this makes more sense. Okay, so how we look at this now is that we have fn less than equal to k times gn. So this k essentially is a blank for us for every n greater than n naught. This essentially is a blank for us. If we are able to fill these two blanks such that this holds, okay, then we can say that fn belongs to order of gn. Okay, so now let's look at some more examples. Okay, so let's talk about some expressions. For example, 2n, then we can have 3n square plus 5n plus 1. Then we can have 4n cube plus 2n plus, let's say, 0.7. Then we can have n square plus 1 plus log n, right? Something like this. So let's see. So this belongs to order of n. Let's test this. So we have 2n less than equal to n. We have a blank here. For every n greater than equal to, we have a blank here. Okay. So if we write here, let's say 5, or if we write 5 here and we write maybe 1 here, I think it holds, right? 2n is less than equal to 5n for every n greater than equal to 1. Yeah, let's look at this. Okay, belongs to order of n square. Okay, let's look at this. 3n square plus 5n plus 1 less than equal to less than equal to, let's say, some blank n square for every n greater than equal to 1. Okay, take a guess and see what we can do. N greater than equal to blank, right? So the best way to do it is like you fill one of these arbitrarily. Let's say put 1 here and then you can automatically try to see what fits here best. Okay, so probably something like 10 would do. Yeah, all right. So now what I want you to observe is that if Fn belongs to order of n raised to power k, Fn will also belong to order of n raised to power k plus 1, right? Or higher orders of n raised to power orders higher than n raised to power k will also be asymptotes to Fn. Okay, so we can check this. So what I'm trying to say is that if this belongs to order of n square, this must also belong to order of n cube, right? And you can check this by putting n cube here. Okay, so now let's get, so this was a theory. Okay, let's get more towards the practical elements of that. Okay, so how to apply this knowledge to questions. All right. uh, Fine, so we discussed the case of a simple for loop. Okay, now let's discuss an example. Let's say we discuss something like binary search. All right, so how do we write the function? So it's like bin search. We can just write bin for now, and we can write arr, n is the length, or just let's make it l. Then we can write low, high. Okay, and also we are searching for target. Okay, right. So what happens? So first we take out mid. You can have low plus high minus low by 2. Okay, why we do this and not this, high plus low by 2? Why not this and why this? Is because this can overflow. Okay, 10 raised to power 9 plus 10 raised to power 9 will be something negative. Why? Because it can overflow. It is beyond the limits of integer. Okay, so it's always better to prefer subtraction in this case, which is why I did this. All right, sure. Now we have mid. Then what do we do? If target is greater than ARR of mid, we search the right half. Okay, search right half. Okay, else if target is less than ARR mid, search left half. Okay, else what do we do? We have the answer, right? Else return what? Mid. Okay, so this is what binary search does. We all are aware of that. But how do we figure out the complexity of this, and how do we figure out the complexity of similar natured algorithms? Okay, so let's look at it and try to see. Okay, so we have an array Okay, we pick the middle of it, we check. So this and just checking this are constant time operations. Okay, so checking and finding out the mid is all order of one, which is a constant time operation. So it doesn't really take any uh, amount of time which is dependent on the input. Okay, these are all constant time operations. So the way our function sort of a recurrence relation behaves is something like this. Okay, let's say we have an n length array length of n. So we have f n is equal to, you spend some order of one time in evaluating mid and comparing, and then you do what? You do f of n by 2, right? Why? Because you discard half of the array and you only pick one half. Okay, for example, if this is your array, okay, so if you check mid, if you find mid to be less than your target, you simply check this half and you don't check this half. Okay, so this is why this recurrence relation, time taken to evaluate the entire thing is some constant operation plus what it takes to evaluate half of it, right? Because that is what we are sending in the recurrence. Now what happens is we get log, let's say a recurrence tree, something like this. So we check for n, then say we check for n by 2. Okay, then we check for n by 4, and then we check for n by, sorry, n by 4, n by 8, okay, and so on. All right, so how this helps us in is that we keep on recursively dividing or reducing our search space at checking by the middle element. Okay, sounds good. So if you see at the leaf of this, uh, so over here, as we go down towards the leaf of this, you will have some one when you have just one element remaining. All right, so let's say after some n levels, after some k levels, you reach 1. So what is that? N divided by, so this is basically n divided by 2 raised to power 0. This is n by 2 raised to power 1. This is n by 2 raised to power 2. This is n by 2 raised to power 3. So n divided by 2 raised to power k is equal to 1. Right? Right? So what do we get? N is equal to 2 raised to power k, where k is equal to log of n. So we have log of n levels, right? And at every level we spend this operation order of one time, right? So the time complexity of binary search becomes order of log n. Okay, so this was just a very intuitive and not a very formal proof, but this basically gives you a idea how to solve recursive time complexities or recursive relations. All right, so let's take some more examples. So let's take the example of merge sort. Okay, so what happens there is that you spend you spend some time in merging the array uh, at each recurrence. Okay, so basically your time taken to sort an n length array is equal to time taken to merge, that is order of n, plus twice the time taken to sort half length arrays twice, right? Twice the time taken to sort half length arrays. So what happens in merge sort is basically we divide this into two parts and we sort these separately. Then we divide this into two parts and we sort this separately, right? And then we merge all of it together. All right. Okay. So let's say we have t of n, then this will have t of n by 2. Okay. Then probably we have t of n by 4, right? And so on. Okay. Okay. Until we have what? T of 1. Okay. And as usual, whenever we have a division by 2, we have how many? Log n levels. Okay. By the same argument we derived it here, the same logic. Okay. By the same logic that we derived it here, we have the same thing. Okay. Log of n. So what is this? The height of this tree is log of n, right? So so this is total. So if we talk about these operations, okay, this order of n operation, what do we do? So total at this level we have n by 2 plus n by 2 we have again n by 4 plus n by 4 is n by 2, n by 4 plus n by 4 is again n. Okay, so the sum at each level is always n, and here you can see there are n leaves. Okay, so essentially what we're getting is log n levels and n level of n amount of instructions at every level, so we multiply both n log n. So this is the complexity for merge sort. Okay, again, as I'm saying, this is more of an intuition delivering session than a very formal proving session. Okay, so bear with me and try to grab hold of the intuition that I'm trying to convey. That would be much more helpful in solving questions. And we can always refer your books or videos for formal proofs, okay, using the theorems and all. Okay. Okay, so now this is a question for you. If let's say we have something like for I is equal to 1, I is less than n, I multiply equal to 2, I can have j plus plus. Okay, so what is the time complexity of this? Okay, take a guess or try to think. Yeah, any guesses? Order of n. Okay. Anything else? Log n. Okay. N cube. Okay. Okay. So let's see. So first, it I was 1, then I became multiplied by 2, so it became 2. Then it became 4, right? Then it became 8 until it reached n, right? So again the same thing, 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3 until n. So basically we can say for k times 2 raised to power k is equal to n. Again a similar kind of derivation, and we have k is equal to log base to n, right? Okay, so until here, any questions, any doubts, anyone? Okay, so it is not n cube, it is not n, it is actually log n. Okay, any doubts, anyone? Okay, so one very important thing that you should notice here is that everything depends on n, right? And when it all depends on n, what is the n? What is actually n? So again, to avoid having constants in our medium of expression of time complexity, we always use some relative metric to build our arguments on. So n here is the input size. Size of input, or rather you can say, some parameter that we can possibly use to, which is external, of course. The parameter must be external. It should not be determined by the program itself. Some external parameter that our complexity depends on, or our number of computation instructions depends on. So we can have it as the size of input, or you can also think of it as magnitude of an input parameter. Okay, so in this case it is actually n is the magnitude of this input. Okay, you don't have n numbers here, you have just one number, which is n, and you are expressing the complexity as a function of that number, right? Here here on the contrary, you actually have n numbers to sort. You have an array of length n. Okay, so here it is the size of the input, so it could be both, right? Okay, so we have less time, so let's move on to memory complexity and see what we have there. Okay, okay, so memory, just like time, is actually expressed as in a function of input size or magnitude of input. All right, and usually, given the current trend in the industry, memory is considered much more cheaper than time. Okay, so memory is considered to be much more cheap than time. So most of the companies would be willing to trade off memory to save time. Why? Because they trade off basically some RAM or some extra resources, hardware resources, for saving a lot of electricity, a lot of carbon emissions, a lot of, you know, CPU resource engagement in their data centers. That is why they would always, give away everything to save time, even if it is memory. Okay, so until and unless memory is somewhat like exponential, they don't really care about it. Okay, but of course, we would still want to optimize it, right? I mean, even the memory is cheap, but if we can get a similar complexity with even less memory, we would of course want to do that. And to do that, we want to have a quantifier of memory. Okay, so usually memory, as I said earlier, is more like RAM. The amount of RAM that you allocate to a process is the amount of memory available to that process. Okay, so just like time, memory is also expressed as a function of input or a function of magnitude or size of input, right? So whenever you declare a variable, let's say I is equal to 0, you spend some memory in the from the RAM. All right. When you declare an array, ARR 100, so you spend some memory from the RAM. From the RAM, you use up some memory. Okay. So memory are of, you can say, two types basically: stack and heap memory. Okay. So of course, these two have very different meanings when it comes to operating systems. But uh, I would suggest for now you should try to optimize for both of them. Okay, so I will very briefly try to convey the difference between the two, but it doesn't really matter for you at this moment. Whenever you are asked to optimize memory, most more often than not, you are asked to avoid maybe 2D arrays, maybe 1D array or something like that. Okay, you rarely have to think of uh, things like stack or heap. But okay, so ideally you can just think that heap memory is what we want to avoid or optimize for. Stack is more or less unavoidable most of the times, but still, let's look at both of them. So stack comes from two things. One is local variables, and the second is function pointers, or you can have like functions, invocations. Okay, heap is dynamic memory allocation. Dynamic memory allocation. Okay. So now, if we have something like I is equal to 0, this comes from the stack. If we have something like, uh, let's say j is equal to a plus b, this comes from the stack. Okay, int I is equal to 0 or int j is equal to a plus b comes from the stack. All right, and if you have something like a recursive function, let's say Fibonacci. Okay, so you have fib of n is equal to fib of n minus 1 plus n minus 2, right? Fib of n is equal to fib of n minus 1 plus fib of n minus 2. All right, so when you invoke these functions, they go on the stack, something like this. So you invoke, let's say, fib of n. So here goes fib of n. Let's say n was 5. So fib of 5 goes here. Then you have like fib of 4 and fib of 3 here. Okay. Then on top of this, you have, for this, you will have what? fib of 3 and fib of 2. Then for this you will have fib of 1 and 2. Then this will maybe return as it is, and this will maybe have fib of 1 and 0, and this will maybe have 2 and 1. This will have 1 and 0, right? Then this will have 1 and 0. This will return as is, this will return as is, this will return as is. Okay, so basically what I want to convey is that whenever you have recursive functions, whenever you have even regular functions, what happens is that a stack memory is allocated by the operating system to the process, and that stack is used to keep a reference or keep a track of whatever functions have been invoked and where we are in the program flow, and if you encounter a return statement, where to come back to. Okay, as simple as that. So we don't really care about this for now. We only care about dynamic memory allocation. What is that? It is basically something like this. Okay, so when you declare an array, this memory comes from the heap. Okay, if you have used C++ or C, you have malloc. Okay, if you have used Java, you have the new operator. Okay, so the memory allocated using the new operator you have from the malloc function comes actually from the heap. Okay, and this is what we want to optimize for. Okay, let me give you an example where and how optimization works. All right, so let us think of an example. Okay, so let's say you are given a question that take input n and return the prime number greater than equal to n, or just greater than equal to n. Okay, the smallest prime number greater than equal to n. Okay, we have to return that. So one way is to do what? Start iterating from n till infinity, and whenever we check every number for primality, every number, and whenever we encounter a prime number, we return it. Okay, so this takes how much memory? We do not maintain any array or any matrix for that matter, so this has constant time memory, right? And how much is the time? So this could be potentially go up to n. Okay, so n numbers we're checking for, and for every number, primality testing would take how much time? Okay, the brute force primality testing would take how much time? Root of n time, right? Okay, this takes n root n. So time, memory. Okay, now imagine a situation where we store all the prime numbers up to a very big number, let's say up to 10 raised to power 9. We store all prime numbers in one array. Okay, and then when we get n from here, we simply do binary search on this array and try to get the next or successor of n in this array. So memory required is order of n, let's say, and time required is order of log. Okay, so you see how we trade off time for memory, right? So this is a binary search. Okay. So yeah, store all primes and then binary search. All right. So we could reduce the time for answering queries from n root n to log n by trading off memory, right? Okay. If you have a question like how is this order of root n, then we can discuss that, or we could stop here. If everyone is good, or if you have some questions, anything to say or something, we can discuss that. Otherwise, I think they have a quiz planned for you, which you may attend, and let's see what you have to say. Okay. So anything was not clear, anything which you felt was not very well explained, or something which is left out that you feel is still not understood by you, you can point it out right now. I will be very happy to repeat that or discuss that again. Okay, any kind of assistance if you require to understand this topic, let me know. Anyone? Any problem? Okay, then I think we are good. So, okay, so whatever I have explained, or even beyond that, if you need anything from me, any kind of support, and if you think I will be able to help you for something, okay, then do not hesitate to reach out to me. Okay, you can find me up on LinkedIn if you want to connect, and rest I think is good. Okay, so anything, any kind of assistance regarding your interviews, regarding uh, any preparation strategy, or okay, yeah. So for ICPC regions, I would suggest you practice for speed as well as for accuracy. So code forces, gym, and problem sets are a good way to do it. If not, of course, I mean you have to begin with simpler things, but eventually you should be well versed with code forces. That's I think the best resource for ICPC. And if you're able to solve at least like 3 questions on a code forces division 2 contest, it should be good, at least for a good start to ICPC. All right, and then of course there is no end to it. All right, so code forces is Russian, at coder I think is Japanese. So yeah, both of the countries are doing well in ICPC. Yeah. Okay, so I would say just pick up concepts, attend contests on code forces and other places as well. And when you pick up concepts, try to solve problems around those concepts that can help you actually get some hands-on on those areas. Otherwise, uh, it would mostly be just reading concepts, or maybe it might get boring. So the best way is to pick up concepts, understand them, watch a couple of YouTube videos, look at some blogs around it, and try some problems. which you have not tried before or not read about before. Another way, another good way to do about is go about it is that whenever you uh, attend a contest, try to solve the next question. For example, in the contest, if you were able to solve A, B, and C, try to solve D, and if not E, at least D on your own after the contest ends. All right. And if you're not able to do that, check out the tutorial and try to gather what you can learn from that question. So even if you have upsolve one question, it should be a very big improvement in you in the long run. All right. So that's all. If you need some more help on anything, some advice or suggestions or recommendations or anything which you think I can help, whether it be higher education, internships outside of India, research internships or industry internships, or placements or whatever, just let me know. Even if it is competitive programming, ICPC, GSOC or whatever. Okay, whatever you think I can help you with, I will be happy to you know guide you for that. Okay. If no questions, then I think we can end this. And you, I think, have a quiz lined up for you. So yeah, all the best.
Thank you so much, sir. It is already proved that you are the true mentor and best guider for all of us. Thank you so much for sharing all the resources for our future. I hope you all enjoy your all energy and hunger to learn something new is worth it. On behalf of DSA Carnival 2K 2020 team, I, Sarika Purohit, thanks you all for being joining us on this fourth star of DSA Carnival session. I would like to thank all our team members, our title sponsor, Geeks for Geeks, and our education partner, Coding Minutes, and all other sponsors for being part of DSA Carnival 2K 2020 team. Guys, this session isn't over here. You will get an quiz link to test your understanding for this today's session. It will be open for 10 minutes and definitely our top rankers will get some cool goodies or swags. So, are you ready to grab your swags? Hey, you should give it a try so you can be a top performer. This session is already proved a splendid learning session for all of us. Thank you all the audience for enjoying this session. Stay tuned guys for next upcoming sessions. Thank you.
So you think you know data structures well, but often get stuck when it comes to problem solving. Well, now you are at the right place. Welcome to Data Structures and Algorithms Level Up course. Hi, my name is Prateek and I'm a software engineer at Google. I have created this course for anyone who wants to learn how to apply data structures for solving coding problems and algorithmic optimization. In the past 5 years, I have taught over thousands of developers through my online and in person bootcamps that helped many students and working professionals in their careers immensely. This course will help you to develop a strong problem solving mindset and write cleaner and highly optimized code. This course is a highly practical course and we will discuss over 100 problems of varying difficulty levels along with a complete hands on implementation. You will learn various tips and tricks related to concepts like recursion, backtracking, sliding window, two pointer problems, dynamic programming, pattern matching, graph algorithms, and more. Not just that, you will also learn by solving problems involving various data structures such as stacks, queues, linked lists, heaps, hash tables, tries, and graphs. With over 200 plus high quality video lectures, concise and simplified explanations for complex topics, this course is your one stop destination to master problem solving. Unlike most other courses, this course is fully interactive. You also get coding exercises and multiple choice questions to test your skills. The code judge ensures that your logic is correct and you get a real time feedback on your code submission. Doesn't matter whether you have a computer science background or not. This course is for anyone who wants to ace problem solving and achieve big. So what are you waiting for? Sign up today and I'm looking forward to meet you in the course.